We're going to finish off this section with a few special cases. Now, I'm not going to prove these theorems formally, but they're pretty easy to see what's going on here. Okay, so let's take this theorem here. If A is a square matrix, then the determinant of the transpose of a matrix is just the determinant of the original matrix. So let's take an example, and you can see why this might be true. So let's let A be the 3 by 3 matrix with elements 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, and then we know that we could take the determinant of this by expanding along the first row, for example. Okay, 1 times the determinant of what's left, right? And then 2 times the determinant of the elements left over after canceling the row and columns. 3 times the determinant of the elements left over after canceling the row and columns, and so on, right? So if I take the transpose, all that happens is I swap the rows and columns. So the first row becomes my first column, the second row becomes my second column, the third row becomes my third column. And we know that taking a determinant, we could either expand along each row or each column. So instead of expanding along the rows, what if I expand along the first column of A transpose? Okay, then canceling out each row and column of each entry along the first row, I'm going to get exactly the same thing. All right? So expanding along the first row of A is exactly the same as expanding along the first column of A transpose. And if you actually want to work it out carefully, you could see exactly what's going on there. Okay? So the determinant of a matrix and the determinant of the transpose of that matrix are equal. Now let's talk about triangular matrices. If A is a triangular matrix, then the determinant of A is equal to the product of its diagonal entries. So first off, what is a triangular matrix? So there's two kinds of triangular matrices. A lower triangular matrix. Lower triangular matrix would be a matrix like this, where everything above the main diagonal is 0. Okay, in other words, the only non-zero elements are in this lower triangle of the matrix. Okay, we call that a lower triangular matrix. An upper triangular matrix is the same thing, but now the triangle is in the upper top right corner of the matrix. So everything below the main diagonal is a 0. So now we've got the only non-zero entries are in the upper triangular portion. Okay. So why is it that the determinant of a triangular matrix is equal to the product of its diagonal entries? So the determinant of this lower triangular matrix should just be 1 times 2 times 3. Super easy to find the determinant of a triangular matrix. For an upper triangular matrix, it's a triangular matrix. So its determinant is just the product of its diagonal entries. Again, in this case, 1 times 2 times 3. Those are the entries along the main diagonal. So to see why, let's expand along the lower triangular matrix. Let's find the determinant. Upper triangular is pretty similar. Let's find the determinant of this matrix by expanding along the first row. Okay, so if I expand along the first row, I get 1 times the determinant of what's left, right? So 1 times the determinant of 2, 0, 5, 3. The other elements in the first row are 0, so I don't have to worry about them, right? They won't contribute anything to the determinant. Just going to be minus 0 plus 0. So this is the determinant. right? Now to find the determinant of the 2 by 2, I'm going to take 2 times 3, and then minus 0 times 5. So 1 times 2 times 3, and then 0 times 5 is just 0. So I don't have to worry about that. So I just get 1 times 2 times 3. Okay? 1 times 2 times 3. The reason why this works is because at each step, for a lower triangular, you could expand along the top row, and all but the elements along the main diagonal are 0. So the only non-zero element here is the element along the main diagonal, right? So we expand along that. When we had to take the determinant of a 2 by 2, if you expand along that first row, the only non-zero element here is the 2. If you use a larger matrix, the case is similar. If you did an upper triangular instead of a lower triangular, it's almost exactly the same. You would just expand along the columns instead of the rows. Okay? So if we have a triangular matrix, you can find its determinant just by multiplying the entries along its main diagonal. Okay? And so we can use that result to prove this corollary that the determinant of the identity matrix is 1. So the identity matrix has 1s along its main diagonal and then 0s everywhere else. Okay? Notice what that means. That means that the identity matrix is a lower triangular matrix. Everything above this triangle is zeros. The only non-zero elements are in this lower triangle. But also, the identity matrix is an upper triangular matrix. Right? Everything below this main diagonal is 0. The only non-zero elements are in the upper triangle. In fact, it is both a lower triangular and an upper triangular matrix because the only non-zero elements are along the main diagonal. We actually call this a diagonal matrix. A diagonal matrix is a special case of a triangular matrix. Okay? But because it's a special case of a triangular matrix, all we need to do is multiply the entries along the main diagonal to find the determinant. So the determinant of I just need to multiply the entries along the main diagonal, so that's going to be 1 times 1 times 1 times 1. If I just multiply a whole bunch of 1s together, I'm just going to get 1. And so the determinant of the identity matrix is just 1.